Think about it for a second. Building a spacecraft is arguably the absolute most unforgiving engineering challenge humanity has ever faced. I mean, a single miscalculation, a billion-dollar mission literally evaporates in the vacuum of space. Welcome to The Explainer. Today we're diving into exactly how NASA prevents those catastrophic failures by taking vague, kind of messy ideas and turning them into space-ready reality. We're going to explore the 5 foundational systems engineering processes used in the earliest phases of NASA projects. These are the pillars that allow brilliant engineers to define what a system absolutely must do, how it's going to do it, and what success ultimately looks like. All right, let's just tackle this massive question right out of the gate. If you are tasked with building something as incredibly complex as a lunar lander or, say, a Mars rover, how do you systematically build it so it doesn't fail? Where do you even begin when all you have is a rough concept and a room full of stakeholders who all have completely different expectations? We're talking about projects with billions of dollars on the line, millions of individual, highly sensitive components, and absolutely zero margin for error. You definitely can't just start bolting metal together, right? Well, the secret lies in what we can call the blueprint to reality funnel. This is a 5-step, highly interconnected process that takes us from those messy human expectations at the very top and meticulously filters them down to a concrete physical design at the bottom. And let's be real, human expectations are incredibly messy. You might have scientists who want maximum sensor capability to get all the data, but the engineers know they have to keep the spacecraft light enough to, actually launch. So these steps aren't just a basic checklist. They're tightly linked, they loop back on each other, and they constantly work to balance out those competing demands. So here's our roadmap for today's explainer. We'll be looking at scope, CONOPs, requirements, logical decomposition, and finally, the design solution. Let's get into it. Starting wide at the top of the funnel with Phase 1, the boundaries, or defining our scope. What's really interesting here is how surprisingly strict NASA's official definition is. They view scope not just as a planning document, but as building the project's explicit fence line. You have to know exactly what is in and, honestly, more importantly, what is out. It's your ultimate contract with stakeholders. If your mission is to map water ice on the moon, that strict intent is your focus, because without a firm fence line, you inevitably invite scope creep. It's kind of like deciding to add a 3rd floor and a swimming pool to a house when the foundation is already poured. It just leads to misaligned expectations, spiraling budgets, and inevitable delays. To build that really firm fence line, you've got to clearly define these 6 elements. You need your why, the objectives, and your what, the deliverables. But I want to highlight 2 absolutely crucial ones: boundaries and constraints. You must strictly map your boundaries so you don't absorb unbudgeted work, and acknowledging constraints, completely non-negotiable, especially in space exploration, where mass limits are totally unforgiving. If your rocket can only lift a certain payload, every extra ounce is a massive problem. You've also got to rigorously document your assumptions and clearly define acceptance criteria so everyone actually knows when the job is done. Okay, once that fence is built, we move to step 2, the story, also known as CONOPs. Now, the crucial thing to grasp here is that a concept of operations, or CONOPs, is not a highly technical document. It's actually a user-oriented, day-in-the-life narrative. It helps uncover hidden needs way before any code is written or hardware is assembled. It explains how the system will be used, who's going to use it, and under what conditions. It captures the nominal operations when everything goes perfectly right, but critically, it maps out the off-nominal scenarios too, like what exactly happens if a solar panel fails to deploy on day 2? Does the spacecraft automatically go to sleep? Does it fire a backup mechanism? Writing out this story is how engineers organically discover requirements they didn't even know they needed. So, if the CONOPs is the story, Phase 3 translates that story into the formal rules of the game. Enter technical requirements. The difference between what and how is so vital here. Functional requirements are the blueprint of tasks, the essential actions a system has to perform. Think of it like simply saying, we need a way to steer the rocket. But performance requirements, those are the ruthless yardstick. They quantify exactly how well it must do that function, stating, for example, that the engine steering mechanism must pivot exactly 9 degrees, with a microscopic margin of error of just 0.1 degrees. You literally cannot verify requirements unless it is written to be perfectly, undeniably measurable. And history tells us that tiny errors in these rules can cause massive, catastrophic failures, like million-dollar probes crashing into planets, just because of simple math mix-ups. No way we want that. To avoid it, every single requirement has to pass this strict,
8-rule checklist. A requirement isn't just a fun idea. It has to be necessary, verifiable through rigorous testing, achievable within physical limits, and totally unambiguous. It must be complete, consistent with the other rules, and traceable back to a real stakeholder need. Finally, it must use binding shall language. You know, engineers absolutely love the word shall because it's legally and technically binding, unlike fuzzy words like should or might.
All right, moving right along to step 4, the blueprint, or what we call logical decomposition.
This is where we systematically break down what the system must perform and map out all the information flows between subfunctions. But notice the key constraint here. We intentionally avoid picking specific hardware. We are not choosing vendors or form factors yet. So why is this such a genius move? Well, because locking in hardware too early is a classic project killer. Technology changes rapidly, vendor supply chains break down, but the core functions your spacecraft needs to perform, those don't change. We're simply taking a top-level requirement and distributing its functions across lower-level logical elements. The entire purpose of this step is transforming an abstract idea, like, say, maintain orbital stability, into a concrete functional roadmap. We break it down into precise subfunctions like measure attitude, calculate attitude error, and generate control signals. It's basically like mapping out the entire nervous system before you ever start building the physical body. This highly structured path guarantees that no requirement gets lost along the way, ensuring we fully understand the system's behavior before a single dollar is spent on buying actual parts.
And that brings us to the very bottom of our funnel, step 5, the reality, our design solution. This is the moment we finally commit to how we're going to physically build this thing. We take all our architectural alternatives and brutally evaluate them using trade studies. In systems engineering, there are rarely perfect answers, just optimal compromises. We make highly informed trade-offs between cost, mass, technical risk, and performance. Like, do we use a really heavy solar power system, a limited but super light battery system, or maybe a complex hybrid? We score them, select the preferred physical solution, define all the interfaces, and establish a firm physical design baseline that the team can actually go out and build. So as we wrap up this explainer, I want to emphasize that these 5 foundational pillars, scope, CONOPS, requirements, logical decomposition, and design solution, they aren't just for space exploration. They represent an absolute masterclass in disciplined problem solving and conquering chaos. So I leave you with this. Whether you're building a lunar lander, launching a massive new tech platform, or completely reorganizing a business, how will you apply these 5 pillars to turn your own abstract visions into reality?